Good afternoon and welcome to another session of the Digital WE Days. My name is Jon and I will moderate this webinar today. Our topic of today is how capacitor measurements and specifications can help you select the correct capacitor. Our speaker today is Jon Izkue Rodriguez. Jon, hi, cool to have you here. He will hold the presentation and after that he will answer your questions. Capacitance is just the beginning. Datasheets reveal much more. But how do you decode ripple limits, derating and ESR? Let's clarify the details. Stage is yours, Jon.
Thank you, Silas. So, hello and welcome also from my side. Now you can see the agenda for this presentation. The general idea is that we will speak about some specific aspects of capacitor selection, and for this we will look at some measurements that maybe you are not aware of, and also some details in the datasheet that you have to understand to select the capacitor for your application. So I will talk specifically about some aspects of MLCC and aluminum electrolytic capacitors, and then some other general ideas, and then I will show you how it works, how you can find this information in the datasheet and RedExpert. So first of all, this is our portfolio. At World Electronic, we have a wide range of capacitors, capacitor technologies. As you can see in this image, voltage and capacitance ranges. You can see that we have a wide spectrum of MLCC in gray, but also for high power, we also include the thin capacitors, including the high voltage, high capacitance DC link capacitors for high power applications. As well as in the right side for aluminum electrolytic, you can also find bigger size electrolytic capacitors, including snapping and electrolytic capacitors with screw connections. In the far right side, you can see the supercapacitors, which have a very low voltage rating, but we have from 3 to 350 farad ratings. And before we start, I want you to know about RedExpert now, because I will talk a lot about RedExpert in this presentation. Now we have already launched the survey. This is for us to understand how deep you know about RedExpert. This is our online selection tool for the whole World Electronic portfolio. And this is a browser or it's a website application that is free to use. You only have to register to unlock the full functionality. And for this, you can also use the new WE ID, which will also unlock other functionalities for the supply chain. And in particular, about capacitors, we have 6 modules, which include all of our portfolio. So ceramic capacitors, aluminum capacitors, including polymer and hybrid, safety capacitors for mixed applications, DC link and DC film. So 2 modules for film capacitors for DC and the supercapacitors. So thank you. I am already seeing the survey and looks good. So it seems most of you either don't use RedExpert or you use it, or you know but you don't use it. So this is a perfect presentation for you, so that you can take advantage of all this information that we provide you. Thank you, Silas.
Yep.
So we will start with the ceramic capacitors. So maybe if you have been designing with MLCC class 2 capacitors, you have seen this kind of curve. This is what we normally call a DC bias curve or DC voltage dependency curve. So you can see that for some MLCC class 2 high capacitance types, the capacitance is more or less the rated value at 0 volt DC, but in the moment you load with DC voltage, you have a loss of capacitance. And in this example that I show you, you can see four ceramic capacitors with 1 microfarad and 50 volt. But all of them have different size, and you can see the blue one is a 1812 size, so it's quite big, and it has a capacitance drop, I don't know, around 700 microfarad, nanofarad. So it's losing 30% more or less at rated voltage. And in the worst case, we have 0805 size, so quite small in comparison. It's about 20 times smaller. So you can see the capacitance is much lower at rated voltage. So as you can see, this effect is heavily dependent on the size of the component. So this information is not in the datasheet, and this is why we include this information in RedExpert, and I will show you now how you can find it. If we go back to the datasheet, this is normally what we have in the first page, and this is normally the table that you are looking at. So rated capacitance is right here, and it's 10 microfarad in this case. And it's important that you understand that this is measured at 1 volt and 1 kilohertz, and 0 volt DC, and this is not written but is implied. And you have to read this part. This is why it's included in the main table. You have to read these test conditions, because we are also specifying that we are measuring this at 25 degrees, so room temperature. We also include in the same table this sentence about preconditioning class 2 capacitors. Why we do this? Because to get reproducible measurements, we need to reset the ceramic material. When we measure it for the first time, you get the red curve that you can see here after the preconditioning. But if we measure it for the second time, we get the blue curve. So because the material was already polarized once, there is a memory effect, and there is a permanent capacitance loss. I have this animation to show you what happens when we measure DC and also go in the negative range, and you can see how every time if we do this curve, this sweep, we get all the time different measurements. So we only consider the valid one when we have measured it for the first time after the preconditioning. And this is 1 hour at more than 150 degrees, and then waiting 1 day to measure. Why does it happen? So when we have, this is a simplified structure of a MLCC, we have very small dielectric layer, which is filled with ceramic, of course, acting as the dielectric material. And I can show you how it looks like in reality. We have a more or less regular uniform grain size, and in these grains we can also represent this like this. When we have a DC voltage, these cells are divided in domains, and the domains have a electrical polarization, and we have a orientation of all the domains in the same direction, depending on the electrical field generated by the DC voltage. So it looks like this when you have used DC voltage, but when we measure it for the first time, we don't have this polarization. So another aspect that maybe you have seen in the datasheet is that we specify a AC level. So the AC level is 1 volt in this example, but if we vary this AC level, this is a setting of the LCR meter. You can see an example of a LCR meter in the image. Actually, if we have very small signal, the capacitance may be smaller. And if we have a high signal, sometimes it goes up, sometimes it goes up and then down. What you can see also is that for most of the small signals, if we represent it in a logarithmic axis, the voltage, you can see it's quite uniform for small signals up to 100 millivolt, then it goes up. So in the specification, we go we have a quite big signal. So this is advantageous for us to say that this is a 10 microfarad capacitor. But of course, if you have a small stimulation signal, you may have less capacitance that you expect. Again, this is the information that you can find in RedExpert. Why do we have this kind of stimulus signal, which is very high, but also a very small frequency? Why at this frequency? This is because in this kind of LCR meters, what we do is we generate, let's say, 1 volt, 1 kilohertz, and we want to have this signal at the DUT. But there is a series resistor, so the stimulus must be higher so that we have the 1 volt here. This is monitored with this loop. And if we measure at high frequency, you can see that the impedance of the whole capacitor is so small that imagine if to hit 1 volt here at 100 kilohertz, compared to, we have around, I don't know, 0.2 ohm. So compared to 100 ohm, it means that we have to generate a signal. To get 1 volt here, we have to generate, have here maybe 100 to 1000 volts. So as you can imagine, this is impossible to handle for this measurement equipment. So what we do is we measure at very low frequency right here. And here we have 20 ohms. So it's manageable for the device to compensate for the series resistor. And this is the reason why we have this, this low frequency. Again, this maybe is not related to your application. In your application, maybe you have a switch mode power supply. So maybe you have a switching at 50 kilohertz, maybe a ripple voltage, maybe of some, or maybe hundreds of millivolt. So it's totally different. Also, the temperature is different than room temperature because probably the capacitor is getting warm from other components. Again, this is another example of what happens when we measure it at high frequency. Actually, the signal is not so different, but we cannot go so high in the voltage because the measurement device doesn't allow it. But as you can see, we have a lower capacitance than we have specified, which will be here. Again, I repeat about the AC level. If we see this curve, the red one is the same as I showed you before, but it's another component. And you can see it's quite, maybe the capacitor is specified here, but at low level we have this. But what is the relationship with DC bias? Well, actually DC bias is what matters really. So if this 10 volt capacitor is measured at 5 volts, so half rated voltage, we already lost so much capacitance that it doesn't really matter how much AC level you have. At full rated voltage of 10 volt, we lost more capacitance, and it doesn't really matter which AC level you have. So you have to consider this 22 microfarad capacitor at 10 volt, and with a small signal, it's only about 2 and something microfarad. So this is important that you understand. The same curve, but maybe reverse it. If we have the DC bias curve and we are switching, measuring but with different signals, also small signals, 1 millivolt, 10 millivolt, you can see, yes, it matters when we have low DC voltage, but it matters very little if you have a DC bias. So DC bias, DC bias is what really should worry you, and this is the curve that you have to look. A similar thing happens with temperature. So maybe you have seen this kind of curve, and DC bias is again DC bias curve, but we have measured at different temperatures, and you can see, yes, at 0 volt, yes, we have very different capacitance. But when we include also DC bias, there is, let's say, a saturation of the material, and then we can see that DC bias is what really matters. But so the effect is not adding capacitance loss, but is converging. Again, some information about these are not so relevant in this presentation. Yeah, and there is another effect that you have to understand, again related with this saturation, is that if we keep measuring at voltage, maybe rated voltage, we can see over time that it will keep dropping capacitance. So for example, after 10 seconds, we have maybe 50% capacitance loss in this example. But actually, after 1 hour, we have lost more, even more, another 15%. And after 24 hours around, we have lost additionally 20% more. So you have to consider this also in your application. For this case, I recommend you do your own measurements because it takes a long time. But it's important to consider if your application is switched on most of the time, then you can expect that the capacitance will keep dropping. We have not seen a significant drop after 100 hours. So we consider after 100 hours that it's already saturated and will not keep dropping. But this is an effect that has to be considered in your design. Finally, this kind of measurement, impedance measurements, ASR, DC bias, what I just commented, we do this for all of our part numbers. And what we do with this is that we generate models for the simulation. So you can add these models in your simulation package. We have it in LTSpice, PSpice, and much more. And we also include DC bias in our simulation models. So both curves are modeled in this example. I mean, in this example, the capacitance is permanent, is constant, but we have a model which includes the DC bias effect. And finally, as I already said, all these curves are in the DexPert for you to consider and also to create, if you prefer, your own simulation models. I will show you now in the DexPert. You can navigate like this to the ceramic capacitor module, and as you can see, you can filter pressing these buttons. And in this example, I filter for 1 microfarad, and I can set another filter for voltage range. So maybe 10 to 25 volt parts. And now I can also sort the table. I have sorted for higher size, and like this you can select different components, and for each component that you select, you can see the curves in the bottom to compare different components. As you can see, you can also move these sliders, and in the moment you set a slider, for example in this case 5 volt, you get in the table, you get the values from the curve. So yeah, to the next topic about electrolytic capacitors. We have the same idea. Actually, in the datasheet we have this table. This is most of the information that you need. Test conditions all included, including in this case the ripple current, which is rated at maximum temperature and 120 Hertz. So we rate the component for a maximum of 900 milliamps of ripple current, RMS. But if you navigate to the page 2 or 3, you can see this table. In this table, we have marked this part. These are multipliers that we include for capacitors. When you have a switching frequency that is higher, maybe you are allowed to have a higher ripple current. So this is what it means, the multiplier for ripple current. Another table that we include sometimes, this we include mostly for the bigger sized electrolytic capacitors like snap-ins or screw capacitors. We include this table, and what it means is, yes, at maximum temperature, you have the rated ripple current, but at lower temperature, you actually can have a higher ripple current. This is because we allow for more self-heating of the component, but you have to consider that this will affect the lifetime because it's heavily dependent on temperature. So in this example, the previous example, maybe we are switching it at, instead of 100 Hertz, we are switching at 20 kilohertz, and we have a temperature around 60 degrees. So instead of the 900 milliamps, we have now, including both multipliers, we have almost 2 amps. So it's, yes, more than 2 times the ripple current that we allow it in the datasheet. So you have to consider this also in your selection. So how do we do this calculation in RedExpert? I can show you. Again, this green button means I have logged in. So I have unlocked all of the functionality, and I select the electrolytic module. So now I am filtering again only components from 400 volt rating, and the capacitance, for example, I think I filtered 100 to 300 microfarad. Now I have a big list because we have many components that fulfill this filter. So what I can do now, instead of looking like this, I can set the slider as I showed you before. For my application, maybe again 20 kilohertz and 60, maybe 70 degree in this case. So you can see now the ripple current that I showed you before is already including a new column with the calculation for the multipliers. So now I can sort the table for higher ripple current, and now I can, for example, select these 3 components that are the ones that fulfill the filter, but also have the highest ripple current at these specific conditions. Now, in the table, there is something I jumped, and it was the lifetime performance table. So I will explain. The most important thing is in the middle. It's called endurance, and this is what this is the name of the test that we do to check the lifetime of the component. So in endurance, you can see the testing conditions are the hardest. So we have the maximum temperature, maximum voltage, maximum ripple current. And in these conditions, after 2000 hours, so this value changes depending on the part number, we can expect that we fulfill these conditions. This is what we call the endurance conditions. So we can expect only to lose 15% of the initial capacitance, and the ESR is only allowed to go up to 175% higher than the specification. So this is the playing area that we have, the space that we have. Now, in this table, there are other information. For the bigger capacitor sizes, like snapping and screw capacitors, we include the useful life. What is it? We test it at the same conditions, but now we allow for, let's say, more relaxed conditions of passing the test. And for this, we can specify, yes, on these conditions, we actually have 5,000 hours tested. And it's important to remind also, in these cases, we include a failure rate. So it could be that there is a statistically more possibility for failure. Finally, the shelf life is not so important. It's tested only on temperature, not on load. This is why it's called shelf life. And it has the same conditions as the endurance. But of course, this test is always passed because it's always less time and less harsh conditions. But it's important to remember this is, let's say, a delivering aspect. So when you get the components to measure them, you should be able to reform the capacitor, because in this case it is under voltage, but here no. So the conditions are only guaranteed after this restoration of capacitor, which is done on voltage, rated voltage. Now I will show you how you can use the lifetime calculator in RedExpert. So if we retake the same scenario as before, you can see the green component selected, and actually the sliders have synchronized with these input boxes. And in these conditions, I get maybe 2 years for this capacitor under this voltage and frequency and temperature. Now, I am allowed to have up to 3.34 amps. Maybe if I set up 3 amps, I have even less lifetime. Of course, because there is self-heating, so the temperature is higher. Now, in this case, I can select the next capacitor, and with these conditions, I have now 4 years. Why is this happening? This is because this capacitor is actually rated for 105 degree instead of 85. So now this capacitor is, let's say, the lifetime is expected to be much higher at 70 degree. This is because it's rated for the same time, but actually for a higher temperature. And as you should know, temperature is the most important thing affecting the lifetime of electrolytic capacitors. So normally, in this part of the calculator, you can see the endurance conditions, as I have shown you in the table. There was an error as I recorded this video, so it was empty. But normally, you can see this with the initial conditions, endurance conditions, so 50% or 20% capacitance drop, etc. Now, some other tips or maybe insights about what we mean with voltage ratings and what is the impact of voltage on different technologies. So, for example, DC, in this case, film capacitors for DC. In this case, I'm referring to high capacitors for high power, like this DC link capacitors. So these capacitors have in the table, you can find something like this, and it actually says, yes, 1000 volt up to 85 degrees actually, but at 105 degrees, it's only rated for 730 volt. This same information is conveyed in this table or this graph that you can see in the datasheet. So there is a voltage rating, and this is the same information that you can see in the table. And it's important to understand that for film capacitors, and this is a thing for film, specifically about polypropylene metallized film capacitors, you are allowed to have less high temperature but less voltage, or you are also allowed to have higher voltage at low temperature. And this is what we convey in this curve. So this curve, in the x-axis is including the lifetime. This is calculated with a statistical method, and it means that for the same lifetime, what you will get maybe in this 10,000 hours is maybe not that much. You can expect to get the same lifetime at low temperature, high voltage, or high temperature but lower voltage, 70%. This is what we mean. Another thing about rated voltage, when we say rated voltage, we include the ripple or the peak of the ripple that you include. In this case, you can have a high ripple in your application, but you should never surpass the rated voltage rating that we mentioned before. So it is not allowed that you have average at rated voltage. This could mean that the peak voltage is much higher than the rated voltage, and you will probably not have the same lifetime. Regarding MLCCs, the DC voltage has no impact on the lifetime, but as we seen before, it has a huge impact in DC bias, specifically class 2 ceramic capacitors, so X7R, X5R, X6S, and this kind of capacitors. Over voltage, so more than rated voltage, so if you have episodic over voltage situations, you can actually reduce the lifetime because it is possible to have microcracking, and the microcracking will reduce the isolation of the capacitor and may cause it to fail. And this is something that takes maybe time, but if the source is episodic, it's repeating itself, it may create a problem over time. Regarding aluminum capacitors, electrolytic and also polymer hybrids, DC voltage is actually a good thing because, as I say here, you reform the dielectric, you reform the oxide layer that is providing isolation and is providing the separation between electrodes. So leakage is also reduced because the isolation is better. So as I said, performance is not affected. What I mean in this, for the high voltage components, there is a rule that at high voltage, actually the high voltage components have an increased lifetime if you derate a little bit for voltage. So for example, if you have a 450 electrolytic capacitor, but you use it at 300 volt, you can expect a higher lifetime, but it's a small factor, maybe 125%. So about supercapacitors, I didn't mention this before, but actually it's the opposite. Voltage will actually damage the capacitor, and we have a similar situation as the film. You are allowed to run the capacitors at higher temperature than specified, and the voltage can be actually reduced if you want to use it at high voltage, high temperature. But you have to understand high voltage will accelerate the degradation of the electrolytic, of the oxide, of the dielectric layer, and you will lose capacitance over time. So in this graph that we have here, actually at the epsilon axis, or the y-axis, is the temperature inverted, so high temperature in the bottom. And what you can see here is actually reducing the voltage, you will get a better lifetime. The lifetime is the color, or is the capacitance after 10 years calculated. So you will have a better lifetime at lower voltage for the same temperature. So the interaction of temperature and voltage is what is affecting the lifetime of supercapacitors. So as I said, you can derate voltage at more temperature or less. And this also, we have an application note describing this process. So finally, to summarize the whole presentation, I have 3 tips for you. So I recommend that you read the datasheet, and in our company we have we have the service, or the additional service, that we have a datasheet for each part number, and this provides you more information and easy to read. And we recommend also that you read or are aware of the 2nd page, 3rd page, and even cautions and warnings, which are interesting to read in the last pages of the datasheet. We also recommend that you check RedExpert. As I said, it's free to use, and we include much more information in RedExpert than in the datasheet, because this kind of curves is better portrayed in a platform where you can compare different components. And also there are other calculators, for example, the lifetime calculator and other calculators from the other products that we have about power inductors, etc. And another tip is, if you are not sure what you are reading in a datasheet or in RedExpert, you are always free to contact us, contact our sales representatives or field application engineers, which will answer most of your questions. We also have a chat in the website, which will contact us if they are not able to respond, or you can request additional measurements. You can request measurements that are not included in RedExpert. And of course, you can also contact me. You have my email. You can find me, and just instead of interpreting something in the datasheet or and taking the wrong idea, maybe it's better to ask us, and we are here to answer your questions. And now we will answer the questions from the presentation.
Yeah, thank you, Jon, for your interesting presentation. Now we'll come to your questions. Before we start with the live Q&A, I will share the handout from the presentation from Jon. So now you can download it, and then I would say we can start. Yeah, we had a lot of questions in the chat. That's very cool to see. Yeah, I think we can directly start. You can so much in the top. Yep. I would say I start with this one. Yeah, first question. How much should I derate MLCCs to account for DC bias? I have seen 50% recommended.
So yeah, this is typical. So this is a very old rule of thumb. So it's not bad to have general rules, but in this case, this is very outdated. In my example that I have showed you before, we have lost up to 80%, even 90% of DC of capacitance at rated voltage. So if you are following this rule, you are going to be very far from your target capacitance. So how much you should derate? You should derate according to our course. This is why we provide you this information in RedExpert.
Cool, thank you. Then I would say next question. Yeah, it's about a question about the slide 15. I can.
Yeah, I can navigate.
Yeah. What about recovery of the DC bias aging effect? How long do I need to power off the cap for recovery?
This is very tricky. I don't have an answer for this because what happens, as I showed you in the other slide, now if I disconnect the power supply and then I wait, it will not go back and go here, but there will be a permanent polarization. So it will go back to maybe minus 20%. And then when I load it, it will go a bit under. But the question is also how long. The question was how long should I have it switched off? I don't know, because the depolarization will also take a long time. For me, it's important that you understand you have a huge uncertainty when you are working with these capacitors. So you have to calculate for a worst case scenario. So the curve will never look like this when I measure it for the second time. And every time we measure it, it depends a lot of how long was it on, how long was it off, and how much time passed in between. Did it go high temperature? Did it go low temperature? Everything will have a memory effect. And what I want you to understand is that it's a general uncertainty that you have to consider. This is an extreme case because it's a high capacitance type, but I cannot give you an answer exactly for your question. But yeah, just to understand, even if I give you a measurement, it will probably not be the same as happens in your application. You have to account for this uncertainty.
Okay, cool, thank you. Then, next question about slide 16. Is the DC bias aging effect included in the SIM model? Can you reconfirm?
No. Oh, what's happening? No, actually the same slide. In our model, what we have is this curve. So this is taken more or less at 10 seconds of loading the capacitors. So the aging of DC bias is not included in the library because we don't know how long you will have the device on. What you can do is that you can set up your own, let's say, capacitor, taking into account a higher capacitance loss than we have in our model. This is what I recommend. And Also, we have published a paper, which maybe you have seen a link. I'm not sure. We have a application note about this, and I can send it to you if you write an email later or ask again. Maybe I will send you the application note in the email.
Yeah. Okay, then.
Sorry, and also, can you reconfirm? Can you reconfirm? Yes. All the effects, also DC bias aging, all the effects are completely reset when you do this preconditioning, this 150 degree over 1 hour. This is what happens after Curie temperature, so the material is completely reset, the domains, the polarization. Yeah.
Then yeah. Next question from Manfred. Where do I find MLCC simulation models with DC bias?
This is tricky because, for example, in LTSpice, if you use the capacitor selection, when you have set up a capacitor and you do right click and there is a list to select, this is a list with ideal capacitance and ESR. If you want the really good models, you have to navigate to our libraries. Our libraries are included in the contrib folder of LTSpice. For example, you can also download our libraries from GitHub or also from our homepage. They are linked in different places, also in RedExpert. And I think now there is a user guide on GitHub where you can find it's a bit tricky because in LTSpice, as I said, you can do the error and select a component which is not including the full model with DC bias. So you have to check this in this quick guide, or also, yes, ask me, and I will show you how you can use it.
Okay, thank you. Then I would say one last question. This one is...
Yeah.
Okay, from Wilfling, sorry, yeah. What is the reference point for these cap degradation parameters when I want to calculate it for worst case or one temperature only?
It's tricky. So, as I showed you before, yes, one temperature will affect your measurement or your capacitance, but depends in your case how much you are loading with DC bias. So if you have a huge DC bias effect, as I have shown you before with, I don't know, 60%, 80% capacitance drop, if you are in this area, the temperature will have zero effect. And if you are in a less DC bias area, you can find the capacitance against temperature curve in RedExpert. And then you will find, I don't know, maybe a capacitance loss or maybe even a capacitance rise of 5%, 10% minus. So around this area, and you can calculate this together with the DC bias. And this will be a worst case, because as I said, the series of effects, they don't add, they converge with the DC bias, which is the one that is saturating the curve, the saturating the material. So yes, again, very uncertain. So you have to trust. Maybe have a worst case calculation and work with it. You do your own measurements and then see on your power supply, see if the capacitance is dropping more or less than you expected. You can measure this with the ripple current and ripple voltage at your capacitor, so you can calculate more or less.
Okay, thank you. Then time is over, so now we are finished with that session. Thank you very much for your time, Jon, for your interesting presentation and for the answers. Thank you for your attention. I hope you enjoyed it. I want to share the link to our homepage. So we had a lot of other sessions during this week at the Digital WE Days. So just now, yeah, hopefully we see us on our next session. Have a good day and bye-bye.
Bye-bye.